So on the quadratic function door, this is going to be your title. Okay? We're going to make a sketch of the parent function. And what is the equation of the parent function going to be down at the bottom of your door? Y equals, thank you, Julie. Okay. X squared. Well, I'm glad a lot of people knew, and that it didn't seem like it was. Okay, so y equals x squared. And then we want to graph that on that door to show the basic pattern of how that looks. So the way that looks is when you plug in 0, you would get 0. And when you plug in 1, you would get 1. And what do you get when you plug in 2? 4. And then you have the mirror image of that on the other side. So that is our parent graph for our quadratic functions, okay, for y equals x squared. So just take a second and get that on your door. So on the back of the organizer, just a little reminder that whatever your function is, say it's like the greatest integer function, so it has brackets. And if it was a radical function, it'd have a square root. And if it's a quadratic, it has parentheses with the squared, right? Whatever the stuff is, there's inside stuff, and then there's outside stuff. Okay? What kind of changes were happening inside? Horizontal changes. Okay, so inside, I don't know if we already wrote this on there. Did we already write this on there? Is all the horizontal stuff. And all the stuff on the outside of the function, not included in the brackets or the parentheses or whatever it might be, is all the vertical stuff. Okay? And we're going to kind of work from the inside out, meaning we're going to do horizontal stuff, and then we're going to do vertical stuff. Okay? When you work from the inside out, though, you have to be a little bit careful. We are going to make sure that we reflect and compress and stretch. All that multiplication stuff, we're going to make sure that we do before any of the addition and subtraction stuff. So before we shift. Okay? So the adding and subtracting, if you recall, shifted things left and right. So we're going to start inside of the function horizontally, but we'll do any of the reflecting and compressing stuff first, and then we'll shift it. Then we'll be done with all the horizontal stuff. We'll look out at the vertical stuff. We'll do any reflecting, stretching, or compressing, and then we'll shift it vertically, and then we'll be done with everything. Okay? That's kind of how we'll get through the graph. Our starting point for each graph is going to be the parent function. That's why these were really important. Okay? And what we're going to do is we're basically going to go through, and if you've got the printouts, okay, those printouts are going to be due by Monday. Okay, and there's kind of like 6 graphs for each one. And what you're going to do with each graph is you're going to name the vertex point. So whichever point started at 0, 0 for your parent function, I want you to tell me where that point ends up after you've moved the graph all around. Okay? I want you to list all the transformations in the domain and the range. But we're going to do one from each of those, at least one from each of those right now, okay, so that you guys can get to see them. All right? So we're going to start with one from your absolute value, which was a little bit easier to graph. Okay? The reason these were a little bit easier to graph is because with absolute value, we could always factor any number that was inside the bars and make it a number outside of the bars, okay? Which meant we didn't have to ever have horizontal reflections or stretches or compressions. We could always end up with the number outside, which made it only vertical stretches and compressions and stuff like that. Okay? So the first thing I want to do is I want to practice with you guys listing the transformations, because if we can list the transformations, it will make our graphing. We're just going to follow our list of transformations to get our graph. Okay? So 3 things are happening in this equation. There's a 3 that's multiplying, there's a negative that's multiplying, and there's a plus 1. Okay? But we said we're going to start with horizontal stuff, then we're going to do vertical stuff. So first, what horizontal stuff do we have to do? None. There are no transformations occurring inside the absolute value bars. Do you guys see that? X is the only thing inside the absolute value bars, so do you understand that there's no horizontal changes? Okay, Eric? That's a vertical one, okay? So we'll get there in just a second. So first, does everyone understand why there's no horizontal changes? There's nothing inside the absolute value bars except for X. So then we move on to the vertical ones. We're going to list all of our reflections, stretches, and compressions before we list our shift. So what could we list first? Colin? Okay, so we're going to have a vertical stretch by 3. Okay, what else? Claire? Yeah.
So is A less than 1 then it's stretch?
If it's horizontal. So it's different for horizontal and vertical. So for vertical stuff, the number's multiplying out front. If it's vertical, if it's bigger than 1, it's a stretch, and if it's less than 1, it's a compression, but that's not the negative. It's about the absolute value, just the number part of it. Because what is the negative cause for our graph? Okay, good. It's going to make it go down. What do we call that in transformation language? Good. It's reflected over the x-axis, or it's a vertical reflection. And you can write it either way. So my list is going to be like instructions for me. And then what's the last vertical change that needs to take place? Good. It goes up 1. Okay. So how these are going to help you is if you know the parent graph, and I know the absolute value has some things about it that are easier to graph than some of the other stuff. But this is the parent absolute value function. Okay? What I'm going to do is these 3 changes, and then I'm going to have a new absolute value graph that shows this equation instead of the parent function. Okay? So the first thing I'm going to do is I'm going to vertically stretch by 3. What that means, your vertex does not go anywhere. When you're stretching or compressing, everything is being moved towards or away from the vertex. It's like your rock. Okay? Things are getting closer to it or further away from it, but it's not moving. So this point is going to be set. Okay? It doesn't move until you shift. So it doesn't move with a reflection, okay? Stuff like that. If we're vertical stretching, what we're doing is picking a point where we knew where it was before, and we're thinking only about the vertical distance. So it is not going to move left or right. It is still going to occur at that place on the x-axis, nowhere else left or right. Okay? But we're going to say the distance before used to be 1. I am now vertically stretching it by 3, which means I'm taking that distance and I'm multiplying it by 3, which means the new distance between those 2 points should be 3 units. Okay? So my vertex isn't going to move. This point is not going to move left or right, but instead of the distance between the vertex and that point vertically being 1 unit, it should be now 3 units because I multiplied it by 3, which means 1, 2, 3. That point should now be here. Okay? Same with this one, okay? It was 1 unit away. If I multiplied that by 3, because that's my stretch, I want it to be 3 units away vertically. So instead of it being right there, which is just a distance of 1, I want it to be a distance of 1, 2, 3 units away from the vertex. Okay? This point, if you're having a little bit of trouble understanding that, just look at it one more time with one other point. Okay? If you looked at this point right here, how far vertically is that from the vertex originally? Just vertical distance. 2 units, right? So with our stretch of 3, we take 2. We times it by 3, which is going to give us 6. This point, after a vertical stretch of 3, should not be just 2 units vertically from where the vertex is. It should be 1, 2, 3, 4, 5, 6 units away from where the vertex is. Okay? So we're looking at this, okay? That's only after 1 change, so that's not my final answer. And you guys have choices. You can either graph several different graphs, or you can make changes as you go on the same graph. Okay? Alex? I'm addressing the negative separately because the negative is a different transformation. The negative is a reflection. So look back at the notes, you guys, on your blue organizer and see that we talked about the absolute value of the number, the A value, being stretching and compressing. The negative part of it is a reflection. Okay, so now that's where this is going to be addressed. Okay, so then we're going to take everything and we're going to vertically reflect it, or in other words, reflect it over the x-axis. So my vertex is going to stay right here because it's on the x-axis. But this point that was 3 above is now going to be 3 below. Same thing on the other side. So now my graph is going to be going downward. All right, and then the last transformation that needs to occur is I then need to shift my graph up 1. Okay? So every point is going to go up 1. They're going to be the same distance away from each other as they were before. So you can see there the final graph. Now I understand we learned like the A, the H, and the K value for absolute value, and that's a little bit simpler, and that's fine, but that's not going to help you with some of the other graphs. You're going to have to learn the transformations, and pre-calc honors are going to be all about transforming graphs. Okay? Any questions on the absolute value one before we try like a greatest integer problem? Yeah. Uh-huh. Mm-hmm. Uh-huh. 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 Yeah. Any other questions on the absolute value before we do? All right. So let's look at the greatest integer one. It was a different graph. So use your blue organizer to see what the parent function looks like. We didn't spend as much time on that one, so you are probably not as familiar. Okay. Now, the first thing is, if you look at the graph right now, what does it look like our horizontal shift is? Helen? 1 to the left. But that's actually not our horizontal shift. Okay? The reason is x has a coefficient on it of 1/4. Okay? That means what's really happening inside the brackets is that 1/4, when it got multiplied to x, it also got distributed to whatever number was also there that represented our horizontal shift. So what number had to have been here so that 1/4 times that equals 1? 4. Okay? So if you have a coefficient in front of x inside your function, meaning you have a horizontal stretch or compression, okay, you need to factor that out before you can see the horizontal shift. All right, so somebody give me the first transformation that we're going to deal with. So horizontal stuff first, and we're going to do reflections, stretches, and compressions before we shift. Good. So it's 1/4, but remember, all the horizontal stuff is a little bit tricky. You always multiply by the reciprocal. So this is a horizontal stretch, which means everything horizontally is actually going to get multiplied not by 1/4, but by the reciprocal of that, which is 4. Matt? Uh-huh. Oh, put the negative there, because it was made by somebody on a Mac. And then. All right. So we have a horizontal stretch by 4. What's our other horizontal change? Helen? Good. We're going to move to the left 4 units. That's going to be all of our horizontal stuff, because that covers everything that takes place inside of here. Emma? Because it's always like x minus h. Remember? So it's always like the opposite of what we think. All right, so then we move on to the vertical stuff. What's the first vertical transformation that we'll address? Claire? Good. A vertical stretch of 3. You guys don't have to write the times 3, but I think it helps like give me instructions on graphing once I get there. I don't have to even look back at the equation. All my instructions are just kind of listed in my transformations. Claire? Mm-hmm. No, like less than 1's like 1/2, 1/3. Yeah. Any fraction less than 1, between 0 and 1. Okay? Alex? Good. Okay. So first we have to remember how our step function started. Sorry, Eric? Yeah, all the boxes are negative, sorry. So how our step function started was it had a vertex point at 0, 0, like every other parent function, and steps were 1 unit long and 1 unit apart, and they kind of followed a pattern like a line with a slope of +1. Okay? So they look like that. I'm only going to put 2 steps on there. The reason I'm going to put 2 is because that way I can change vertical stuff, right? The distance between them, so I at least have another step to look at, but I don't have to redraw like 5 steps every time. Okay? So the first thing I'm going to do is I'm going to horizontally stretch my step by a factor of 4. Now remember, the vertex doesn't change. Things get stretched or compressed towards or away from the vertex. This is our vertex point right here. So that's going to stay, but horizontally stretching it by 4 means instead of being 1 unit long, my step is going to be 1 times 4, which is 4 units long. So 1, 2, 3, 4. Okay? That's how long just the first step would be, which means the second step is no longer going to be where it is right here. Okay? It's going to start where the other step ended. So it's going to go here, and it's going to go 4 units long also. Okay? And that pattern would continue. The next thing I'm going to do is I'm going to move my steps left 4. So now this vertex point will get shifted, and instead of being at 0, 0, it's going to be over here at negative 4, 0. Okay? But still, the steps are going to be 4 units long, okay? And they're still only vertically apart 1 unit. Okay? So I've stretched it, and I've moved it left. My horizontal changes are done. Are we okay with those transformations? Claire?
Why did we move it more positive, but then we said left 4 then?
Because it's always x minus h in here. So the h value is really negative 4. Like when we did the calculator investigations, when it said like x plus 2 squared or x plus 2 in absolute value bars, it was actually negative 2, and it was moving it to the left 2.
So why didn't it stay at 0, 0?
It didn't. This was the end point that was at 0, 0. It was there. So the step started here and ended there, and it just got moved to the left 4. The dark closed point used to be at 0, 0, and now it's over here. Okay? All right, so vertical. Vertical stretch by a factor of 3 for us means the distance between our steps is changing by a factor of 3. But again, this is not going to be affected by the stretch. It's going to stay. So that step is not going to get moved up or down further away from anything. This is kind of like our solid rock step. It's the other ones. So the steps used to be 1 unit apart. That's going to get multiplied by 3, which means I now want them to be 3 units apart. Okay. So my step with my vertex stays where it is, but the step above it is now not going to be 1 unit away from it. It's going to be 3 away. Cody?
So like if it was a negative 3, then would it be negative 3 away from like the
Well, no. So remember, negative is reflection and 3 is stretch. You need to treat them separately. So we have listed, if you guys do this list right, you have every transformation listed here. So we don't change this because of the negative. This is still all about the number value. The negative is what's happening in this next transformation that we're going to do. Okay? So the next right now our steps would appear, there would be another step down here, right? And they'd appear to be going up like this. The very last thing we're going to do is we're going to go ahead and do our vertical reflection. This is on the x-axis, so it will stay on the x-axis. Okay? But this step is not. So it's going to end up getting reflected over the x-axis, which means this solid point is going to end up here. And this open point is going to end up here. So we get the mirror image of what we used to have. Now, you might not think that appears that differently, but it would actually be very different because if you continued this, you would see that the steps now look like they're going in the opposite direction than they did before. And that's the presence that the reflection gives. Okay? Kate's one. Oh, no, not this one. All right, let's look at a quadratic, and then that will be the last one for today, and address this one because it addresses her question with the negative inside of the function. So first, you need to do the same thing. You need to rewrite it with that negative 1/2 factored off of x. What would the number in the parentheses be here? We factored out negative 1/2. This must be negative 2, so that when they multiplied, they make positive 1. Okay? So our transformations in this case, we would now have a horizontal reflection, which means it goes over the y-axis. We'd also have this 1/2. Is it a stretch or a compression horizontally? Huh? A stretch. Okay? So remember, the horizontal stuff is kind of the opposite of what we think. It's a stretch. It doesn't get multiplied by a half. It actually gets multiplied by 2. Okay? And we have a horizontal shift. It says x minus 2. Will that go to the right 2 or to the left 2? To the right 2. Then for our vertical stuff, we have a vertical reflection, and we have a shift down 3.